Hi, Yogesh.
Good afternoon, sir.
Good
How are you?
afternoon. Yeah, I'm fine. Thank you.
Thank you, sir. Thank you for joining us. So I'm making you co-host, so you can be able to share your screen. So
Okay.
participants, now we are in the session third of the day third, okay, of this ATAL FDP program or under the first area 3D printing and design. Now we are having Dr. Y. Ravi Kumar from NIT Warangal. Dr. Y. Ravi Kumar is working as associate professor in the mechanical engineering department at NIT Warangal. He obtained his BTech degree in mechanical engineering from JNTU Kakinada in 2000 and ME in computer integrated manufacturing from PSG College of Technology, Coimbatore in 2002. After that, he obtained his PhD in mechanical engineering from uh, Osmania University, Hyderabad in 2011, and also he pursued done postdoctoral research in 3D printing at Melakau School of Engineering, USA, in the year 2012. He has also supervised more than 30 MTech projects and produced 4 PhDs, and as well as guiding 4 more PhDs currently. He has published more than 60 research papers, sorry, in national and international journals of high repute. He has also filed one international patent and 2 Indian patents in the area of 3D printing. He is instrumental in setting up rapid prototyping laboratory at NIT Warangal. He started MTech program in additive manufacturing in collaboration with Central Manufacturing Technology Institute (CMTI) Bangalore, first time in India of its kind. He has established a world-class metal 3D printing facility at NIT Warangal under TechCube 3 grant. He has conducted more than 15 training programs across India and trained around over 900 participants in the area of 3D printing. So, as well as he also received Young Engineer of the Year 2009 award from the government of Andhra Pradesh and the Institute of Engineers India. He has executed sponsored research and development projects worth of 1.24 crores rupees in the area of 3D printing. He is also life member of ISTE, IE and RPSI societies. He visited many countries like Australia, Sweden, Singapore, USA, France, and Finland also. So this is all about Dr. Y. Ravi Kumar. So I request Dr. Y. Ravi Kumar to deliver his talk in our FDP. Thank you, sir.
Yeah, a very good afternoon, Randolph. First, let me thank Professor Yogesh given me this opportunity, the coordinator of this ATAL FTP. And today is the third day, right?
Yes,
of
sir.
your program. By this time, you might have exposed to certain aspects of additive manufacturing, or otherwise called as 3D printing. So my talk will be on the advanced modeling tools for biomedical applications of 3D printing. So basically, I'm going to cover during this talk maybe next 1.5 hours or 2 hours. So I'm going to deliver this content. So let us quickly introduce this technology. I know this is the third day of the program, so we'll restrict our introduction as crisp as it is. And my talk, basically, it will be focusing much on the medical side. So as we know that 3D printing, it requires a digital data. And where do you get digital data from in a medical domain? So as we know that, so we need to get, we need to get the digital data in the form of a CT or a MRI or any sort of digital data for that matter, maybe with PET or with endoscopy or even X-ray. Digital X-rays can also serve our purpose to start our medical 3D printing journey with the digital data. Normally, that will be with the DICOM image. So, DICOM stands for a digital communication in medicine. So basically, we need to get the information. So that should be read by the 3D printing machine. So for that matter, which you may be using some medical image processing tools, so which we have been using um, tools like uh, software like Mimics, which we have been using it at NIT Warangal, and we do have other medical image processing tools. Then we will discuss some of the medical image processing tools. And one method is going to get a CT MRI scan. So that is for studying the internal geometry or the internal tissue or internal bone or as such internal um, anatomy. So but sometimes in medicine we need to even study the external surface, or we need to say, for example, you need to design some artificial limb. So means we need to design some prosthetic. So for that matter, which we need to focusing on the surface um, capture rather than the internal geometry. So then oftenly you may be using a reverse engineering tools in medicine also, not only engineering practice, especially for the product design stage. Normally you may use a reverse engineering tool. So but here in medicine also we frequently adopt a reverse engineering tools. That's what we'll focus on, the reverse engineering tools also. And either it is through a CT MRI scan data or a reverse engineering digitized point cloud data, but it should be getting converted into a 3D printer understandable language. Typically, it could be an .stl file, or it could be a .amf or .3mf, or typically it may be .obj file. So sometimes some of the 3D printers can understand these file formats. So which we need to ultimately converting your medical raw data sets, the image data or the point cloud data into 3D printer readable format, that is STL. So then which we need to process that data. I hope previous speakers might have talked about that. So I will be focusing much on the medical data image processing, and this is about the soft side of your data, means your virtual model or computer generated model. But why you are looking for a physical model? So that is going to play a vital role as far as 3D printing is concerned. So if you are looking to make some anatomy of a patient, which it has been say captured from the patient, then which we need to make these physical models, then we'll understand what is the importance of these physical models. Then how do you develop a medical application? Then that's also part of my talk. And finally, in order to realize all these, so I'm going to explain our own experience with the medical community people, especially surgeons, oral maxillofacial surgeons, and of course craniofacial surgeons, and of course dental surgeons, some extent cardiac people also. That is our personal experience in the form of 6 case studies I'm going to explain here. And of course, finally, I would like to give the direction, the future direction of this medical 3D printing as such. It may be leading to argon printing or a bioprinting. So that's what I have planned for this talk. So let us get it started with the introduction to the 3D printing technology. So, of course, you may be aware that this technology, as formerly known as rapid prototyping, as we know that it was the designer tool where he or she can quickly make a prototype. That's what rapidly producing a prototype. That's called a rapid prototyping during late 80s or early 90s by the person called Chuck Hull. So he invented a technology called stereolithography operators called SLA, and incidentally he started a company called 3D Systems in USA. So and then that was the journey of this technology has started with the prototyping application. But over the recent developments, so the prototyping application has been elevated to manufacturing application. That's what this technology has been renamed by the additive manufacturing, and then even ASTM has given the terminology and the definition through F42 committee and F279210, and even from the eminent personalities like Terry Hollers. This technology is also say named it as a 3D printing technology. But personally, I do prefer using the word additive manufacturing rather than a 3D printing. Why? Because we are mechanical engineers, so we may be a bit inclined towards say the terminology of manufacturing, the additive manufacturing. So we do even 3D printing is a more common name, so anybody can understand what is a 3D printing. So just it is the extension of two-dimensional office printing technology, maybe through a laser printer or maybe through a inkjet printer. So that is the typical terms normally you come across. But let it be whatever the name you call this technology, but the essence is same, like which either we need to start with the CAD modeling data, so which you have CAD technologies simultaneously with the advent of computers and PCs, and then which you are very much familiar about the CAD CAM CAE tools, and then which your application could be a car, manufacturing a car, or manufacturing a aircraft, or it can be a simple coffee cup, so to sip a coffee. Maybe your application maybe differ from a consumer product to an automobile to aerospace or even medical. So what do you mean by this technology? So as we understood, like which it has to start with the input as a CAD CAM CAE data, or that should be either a surface model or a solid model, and further it is getting say printed, or further it is getting fabricated your digital model into a physical object or a component or a product, and then your application is ready. So that is the typical say transformation from the CAD to the product, maybe by using the additive manufacturing or rapid prototyping or 3D printing technology. So this may be the one way of getting your application, but you may have other situation where you doesn't have a soft copy, or you doesn't have a digital data. So situations are many, like your product designer has sculpted the car body design, so with this innovative thinking, and then with the aerodynamic shape and all. So by using a foam, or by using a clay, that is purely his artistic capability. So then he might have sculpted this design, so where obviously you doesn't have a digital, it is not getting started with the CAD technology, but it is purely a manual or a artistic or a sculpted design, where but we need to get this digital form of this sculpted say product. So then you may undergo some kind of a reverse engineering technique, or a 3D digitizing technology, or a 3D scanning technology, so where you are going to get some about so the medical perspective. So then where do you get your say yeah, where do you get your yeah, where do you get your the digital data? So as we already understood that it is getting um, captured from a patient. Say if you have a conjoined twin surgery separating a conjoined twin, so it's going to be very complex surgery for a neurosurgeon or any surgeons that are getting involved into this complex surgery. So either you take it as an automobile or aerospace application, the complexity customization is the driving force. But similar aspect here, so the complexity in terms of surgical complexity, but in terms of product complexity in case of engineering applications. But you may be say the surgeon may be much worrying about the complexity involved during operation of the conjoined twins operation. So that's going to be the very challenging stuff for him. Why? Because there will be a common neurons and the common nerves and the common tissues where he has to know carefully so detach these twins without damaging much of the tissues. So then definitely it's going to become a very complex surgery as far as a surgeon is concerned. But 3D printing will enable surgeon to say simplify the surgery, and where the surgical precision may be improved, and maybe the operating time may be getting reduced over the conventional methods. So you have a plenty of advantages once you talk about. Let us focus on those aspects. I will try to explain those aspects with my case studies, which we have been performing with our collaborate people from the hospitals. So with this background, say let us focus um, into the general procedure. So what is general procedure that typically you adapt for a medical 3D printing practice? As we understood, like it should getting started with a CT or a MRI scan data. So that's going to be the start point of your medical 3D printing practice. And once you acquire the data from the patient, that is in the form of images. So those images or a grayscale images, and more or less it's a raw data sets, so which it may not convey useful information as far as even radiologist is also concerned. So which we need to make it in useful data, which we need to supplement your data sets, raw data sets, into an useful say model, virtual model. And even eventually that requires for your 3D printing machine, which it should have a three-dimensional CAD model, which it should be say turning out at the end of the day, so which your CT MRI images getting processed. So for that matter, you may be using a different medical image processing tools, which we will be spending some time on that. So by using that medical image processing tools, so then you can be able to reconstruct these two-dimensional images into a three-dimensional model that is very much needed. So it may be an STL file or EAMF, or it may be a .3MF file, but that is very well understood by the 3D printing technology or 3D printing machine. So once you get that 3D model, and I hope the previous speakers might have talked about how do you generate your code, or how do you instruct the machine, then how do you generate the contours, or how do you generate the tool paths. So then once you generate the tool paths, after adopting all the process parameters and adopting all your requirements, or your design for 3D printing requirements has got satisfied. So maybe in terms of support structure or orientation, or it can be say tackling the shrinkage allowance, or tackling the say warpage compensation, or say internal stresses that it has been inbuilt, and then how you can tackle that. So then once you have done that sort of simulation, and then finally you will be sending that data to the machine. And inside the machine, where your say in this case the product could be a skull, or product could be a say a limb or artificial limb, or any sort of say anatomy that you are looking at. You are getting reproducing by capturing the anatomy from the patient, and finally you are going to make a physical model out of that. So then that physical model can be used in several folds. So it can be a simply a diagnostic purpose, diagnostic planning, or a diagnostic model, or even it can be pre-planning model, or even it can be used for implant design and fabrication, or even it can be a device, or even it can be a template, or even it can be a say guide for that matter. Or you may make use of this data even to design and fabricate some customized medical device that should be used during the operation or during the surgery. That is the patient specific um, requirement. So anyway, so that will so we'll come to know that kind of application a very short time. So and anyway, so you may have other applications also, then we'll discuss those applications also, maybe the other applications of this medical uh, say field, like how 3D printing is quite phenomenal. And then if you see the applications of this 3D printing from the source Wallace Associates, where you can see the first share goes to consumer products and consumer electronics together, that is 21.8%. So where you can understand this power of this technology in consumer electronics like cell phone or any other consumer electronics or consumer products, where you need to have more customization, and where we need to focus much on complexity of the product. So then which 3D printing is known for that. So you have complexity is a free of cost, and 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 you have customization, so you have personalization, so and you have nature inspired designs you can fabricate. So you have several benefits. You keep on talking about this technology, but in particular to consumer products electronics, so those are the benefits. And even if you come to a motor vehicle industry, maybe automobile and automotive, so then you may have a different requirements, and you may have a different say tolerances or different properties which you are looking at. So then definitely 3D printing will address those sort of requirements from the motor vehicle industry. So that's what 18.6% share goes to motor vehicle industry. And coming to medical and dental together, so it may be 16.4%. So it is on par with motor vehicle industry. So then one can know the importance of this application. One cannot ignore this application in 3D printing applications. And of course, aerospace applications, which you may come across around 10.2%, and you have industrial business machines 13.4%, academic institutions. This is quite this number is in the recent times it is growing very faster. That's what where our ATAL Academy is also promoting these kind of thrust areas, right? Is even also catalyzing this sort of academic institutions also bringing come forward to make use of this technology. So that is quite phenomenal. And you may have government military applications around 5.2%, architectural applications 3.9, and other applications 3.6. And if you try to say fit all these applications into an Gartner cycle or into an hype cycle. So, which is expectations versus time. If you try to place all these applications, say you have different phases in this as a hype cycle or a Gartner cycle, where you have a technology triggered. That is the initial stage of this technology, and you have other side the industrialization or the plateau of productivity is another side. So where almost your prototyping application is reaching to productivity stage, and followed by non-critical aerospace applications and orthopedic applications. So if you talk about medical practitioners, then none other than orthopedicians or the early users, and then the good amount of people from the orthopedic community, this technology has been used. And then jewelry applications is another area, and home or domestic applications, and dental applications, that is at the most expected or most hyped stage, and critical aerospace applications, followed by architectural applications, sports applications, education, and bioprinting. Coming to medical applications of this 3D printing, bioprinting and organ printing is quite promising in the recent times, and that too it is at the very beginning stage. And medical research and 3D printed clothes and 3D printed houses, or it is in construction industry and military applications, and last but not the least electronic applications. So where you can find any sort of application by using this 3D printing technology. So right now we'll be focusing during this lecture. So everything is going to talk about medical and dental. So we'll confine our talk only that area, not other areas. So then let us first start our medical 3D printing journey. As we know that it should getting started with the medical image data. So this medical image data, so then which it is getting processed. So then you may use, then you may come across different process tools to process this data, the medical image data. So, and of course, which again, we need to draw a line in the data acquisition, medical data acquisition systems, that is before the computers and after the computers. So before the computers means you have, we used to have only X-ray technology to understand or to diagnose the disease, which we need to use to have only X-ray technology, which you may be taking a single cross section at a time, and you will be printing on an analogous film, but you cannot simultaneously say capturing hundreds or thousands of images. But again, thanks to the computers, so you have a computed tomography technology called CT, and you have a magnetic resonance imaging called MRI technology. So typically, what could be the difference between these two technologies, basically CT and MRI? So that differ from your say, what is your region of interest, means your tissue of interest. Say if you are looking for only bony kind of structure, obviously you may be advised to undergo a CT examination. But your region of interest could be a soft tissue like a brain or liver or lungs or kidney, and such sort of soft tissues, and then you may be advised to undergo an MRI scan. But say let it be a CT scan, or even it can be an MRI scan, or even it can be a digital X-ray for that matter, or even it can be a PET, or even it can be a ultrasound, or even it can be a angiogram. But let it come as a DICOM image. So you get the DICOM image. So basically, that is a two-dimensional cross-sectional image, that to a grayscale image. So that to a raw data set which consists of different tissue information by contrasting your say brighter to the darker. So which you have a say 256 number of shades, or again depends what kind of hardware you are using it, what kind of a software you are using it. So even you can able to get a high definition say images. So nowadays your CT technology so have a recent advancements which you can get multi slice CDs at high definition quality of images. So but ultimately it should be getting processed. So why we need to process? Say if you are say you have collected a CT data from a COVID patient, and you want to know the score, the score of um, yeah, the score of the COVID patient, what could be the score, the infection, then you may be interested only the lungs part, but you may not be interested the ribs part, or you may not be interested to the spine and other tissues surrounded by your lungs. But at this point of time, so your region of interest could be the lungs, and how much it is getting infected by the COVID or by the say your coronavirus. So then how much quantity, right? So then you may be interesting about the lungs part, but you may not be interesting at this point of time the ribs or any other surrounding bone or soft tissues. But you have an opportunity here through the image processing tools, and which you can segregate as for your region of interest or as for your tissue of interest. And once you have done that, so that may not be the say goal, right? So your goal could be different. Your goal should be um, anything like say sometimes that dictates your application. So where you are going to use these models. So where you have collected these data, from where the patient you have collected this data, right? So then you may be taking this data to CAD system, or vice versa. You may be say transferring the data from CAD to the medical system or medical image processing system. So then why we need to do that? So we need to design some customized implant or customized prosthetic for a patient specific requirement. So then obviously we need to say travel back and forth to CAD space to the medical image data. And sometimes which your surgeon has to simulate the surgery before he operates in a real time in an operation theater. So which he or she has to do a certain simulation of the surgical procedures. And you might have designed some implant for the femur ball socket joint, and which it will go and fit it onto the pelvis pelvic part. So then we need to simulate this surgery. So then we need to use certain simulation tools which your data has been captured from the own patient, and probably you might have designed some implant, customized implant for this patient alone, and you will be doing performing some simulation of the surgeries. And we do generate a 3D computer models. And sometimes your orthopedician say wants to say perform a failure analysis, like whether your designed bone or your implant, your femur bone is taking all the loads in a real time. So or if your cardiac surgeon or your neurosurgeon wants to perform a CFD analysis, where he or she wants to see the blood flow, say how it is getting pumped, the blood, and so on and so forth, the velocity, pressure. So then obviously he or she say oftenly requires a CFD kind of a tools. But where do you get started your journey? So that is with the medical image processing data. And then finally you may getting printed this physical model. Say you have some tumor and which you are going to operate this surgery, and where you have the physical model with you, and you can perform a rehearsal surgery here onto the real time models that has been collected from the patient data. Or we do design validations. So for say you have developed some implant, we need to design validate it, right? So then you will be doing that, right? So we need to do all that stuff. But where is the start point? The start point could be say your medical image data, so which we need to say, yeah. So and then what are all the tools available for you to perform these sort of medical image processing tools, which it may eventually interface with the 3D printing machine. So then we have softwares like proprietary softwares like Mimics, and we have other softwares like Dolphin, or you have other softwares like 3D Doctor, and you have Simpleware is another software, and like that you may have several softwares. And depends on your availability, depends on your budget, and depends on your say requirement, and then you may adopt these sort of tools. But if you are looking for some sort of open source software or a freeware, and then you can download 3D Slicer as a free of cost. So it will almost all capabilities or the features that a typical proprietary software may have. So but I'm sure you can perform a basic level operations, converting your DICOM images into an STL file, or performing a sort of simulation stuff, but not at the high end level. But at least you can do a reasonable processing of medical data. I'm sure with 3D Slicer is another software which you can make use of. It's an open source software. So yeah, you can adopt any one of these tools that you come across. So that is the start point of your medical 3D printing application. So then you do a reverse engineering stuff in medicine also. So then I think you may be familiar about what is a reverse engineering practice, and what are all the various reverse engineering tools that are available. So first of all, what are the various devices that are available? So what is a basic principle? I hope you may be come across these sort of reverse engineering practice, or 3D scanning, or a 3D digitizing procedure, like which we need to start with a physical model or a prototype or any sort of physical model. For that matter, even it can be a patient, or an human anatomy, or a dry bone, or a cadaver bone. So whatever it is, like which a physical object is there, and which you want to digitize it, you want to say convert that into a sort of say digital information. So then you may use different devices, different sensors, so to digitize or to scan your physical objects into digital form. The digital form, it is getting transformed initially with the point cloud data, and further it is say joined with the triangles, means STL file, and further you can approximate it as a surface model, or a NURBS based model, or even it can be a solid model. And further it is getting used for a CAE application for analysis, or CAM applications, or even it can be a 3D printing application where you have an STL file with you. And then that is a typical reverse engineering which you follow. And you may have a different devices like physical touch probe kind of a stylus kind of a balls to get it capture your say surface onto the object by using a touch probe or by using a non-contact laser beam or even by using a CCD cameras. You can capture the physical objects, or even you have a CT scanner. So basically, what could be the difference between your CT scanner and a 3D reverse engineering or a digitizing system? So probably you may be using for the external surface that is getting scanned, that is getting digitized, and probably you may use these scanning devices. But if you are looking for studying the internal anatomy or internal structure of a patient, maybe skull, maybe brain, maybe a femur bone, maybe any sort of organ that you are targeting to diagnose and to understand the disease, or to um, say know about the malfunctioning of your organ. So probably you may undergo a CT kind of examination. But let it come to these two routes. And you may have a different reverse engineering scanners, so I don't want to get into that. Probably it depends on the size of object and the nature of the object, whether it is the reflective in nature or absorptive in nature, or whether it is a liquid. In the liquid also you can scan. That depends on the nature, the size of the object. So that is getting scanned, and then you may use different scanning devices for that matter, so which you can come across all these scanners. And then how do you get your CAD model or your STL file or your 3D printer recognizable file? So from the point cloud data to STL file, and you may have different softwares for that matter to work on your point cloud data and further reconstructing into a surface model or solid model. So then you may have Geomagics, and you may have Kinet Fusion, and you may have plenty of softwares for that matter, which you can come across as for your requirement and as for your availability. Then you can make use of these tools for reconstruction of this data. And of course, either you come through a CT-MRI route, or either you come through a reverse engineering route, a scanning route. But our ultimate aim is to say convert your physical object, or your patient data into a 3D printer recognizable format, data format. So that is going to be the vital thing. And of course, as we as we are discussing these two methods, either through a 3D model capture, so a typical 3D printing design process and the tools. And I hope maybe previous speakers might have elaborately explained this kind of the methods. How do you get make use of it? So here your model capture, that is through a reverse engineering or a 3D digitizing systems, by adopting some softwares tools to get it capture your data, or through CAD modeling softwares you can prepare your say product, design your product. And then you do a mesh repair. So in order to say rectify any errors in your STL file, the triangular data, the mesh data. And if you are looking some open source tools also, you can find otherwise you can have some proprietary tools to repair this, maybe netfab, mesh mixer, mesh lab, or magix. And you have other softwares to perform this kind of a mesh repair operation. And then you slice the model by using slicer softwares, maybe Cura, Repeater, or even proprietary softwares that is supplied by the machine vendor, can also be used here for slicing your model. And you may even make use of some repositories, online repositories, or digital libraries. So you may have a Thingiverse, or you may use a GrabCAD, and you may use other 3D printing communities as such, where you can access your data as a free of cost, or you can add your models into that community, or you can build up some digital library of these STL files, or any sort of step file, or IGS files, or PRT files, or any sort of VRML formats, or whatever it is. So you may come across all these tools, so that are typically available to process your data. And then which we'll be spending some time on. I don't want to spend much of the time. I hope the previous speakers might have touched up of this STL file and the advantages, disadvantages, common problems, and all. But the STL file is typically, it need not be an ideal representation, but it is a simplest representation. It need not be an ideal. Why? Because in fact, it is not an ideal representation. Why? Because it doesn't support color, it doesn't support texture, it doesn't support material information, it doesn't support file security. So how do you say that it is going to be the best representation? It need not be the best representation, but it is a de facto standard. I do agree, but you may have other file formats which it will enhance the capability of monolithic topology-less STL structure over obj.obj file, which it will support colors, and which it will support precise printing, tessellation data, and even it will support material information. And recently ASTM has come out with an .amf file format, so which is the STL extension, or the next generation STL maybe could be AMF, that is developed by ASTM and ISO together. And even Microsoft indigenously, they have developed a .3mf files. So you can find some converters also from STL to AMF, or vice versa, or 3mf to STL, vice versa. So the ideally what you are looking for, whether it comes to a medical domain, or engineering domain, or any application for that matter. But if it is coming from medical domain, we have to be double cautious. Why it should be double cautious? Why? Because every time you may be either reverse engineering your data, or either you may be say scanning the data from CT MRI, so which that data may not be a foolproof data, or that need not be a watertight model, which it may have a lot of open kind of surfaces. So that, but unfortunately you don't have a mechanism to rectify, or even to identify those sort of errors, whether your contour is a closed contour, that it has been scanned. Unfortunately, your scanning systems, or your medical image processing softwares may not be able to say identify those errors and rectifying them. Identifying is one level of thing, and rectifying them, so that is the next level of thing. So then how do get it, ensure that you have a watertight model, or the model which is free from all errors, right? um, so okay, then that is the software side of it. So then we can keep on talking about the design aspects, or the data formats aspects of additive manufacturing. But let us confine our talk to the medical space, and what is the role of this physical models in medical. So you do have a virtual models, and you do have medical image processing softwares, which is capable of getting a high quality models of the virtual models I'm talking about, the digital models I'm talking about. But still, why we need to have a physical model, right? So a physical model is definitely a physical model, which it will have a touch and feel kind of feel, experience why it is needed for medical application. Say, for example, you have a patient who needs some implant here, so which is of which he broke the facial bone, and eventually it has the orbital rim portion here, and a single specialized doctor cannot operate this surgery. Why? Because it is related to oral maxillofacial surgeon, and an ophthalmologist should also be involved here. um, why? Because if you're not placing the eyeball properly into the orbital rim portion, and he may there is a chance then he may lose his vision because of improper placement of the eyeball into the orbital rim portion. So then one can understand the importance of these physical models. Either it can be oral maxillofacial or orthopedic applications, like where your femoral bone and your pelvic bone and your um, the spine disc or cages, spine cages. So you have the physical models. Let it be any anatomy, wherever your region of interest. So right from the head to the toe. So you have all these physical models. Then if you have a physical model, just now we are discussing, like you can communicate better among the surgical teams, or to educate the patient what you are going to do. You can very well educate the patient, and even these physical models will assist the surgeons with the better diagnosis planning or surgical planning. So what sort of devices or the surgical instruments he has to carry, and where he has to cut. So where those sort of planning the surgery, that before you go into the operation theater, and you do rehearsal the surgery, and you do simulate the surgery once you have the physical models with you. And sometimes, surprisingly, you may come out with an innovative surgical procedure that never had been done. So maybe this may be an opportunity for a surgeon to come out with a surgical innovative surgical procedure, not a routine surgical procedure. And then even it can be used to create a customized prosthetics. So maybe some artificial limbs, or artificial eye, or artificial nose, artificial ears, so which we can even customize them. Those prosthetics can be customized, so that is as for the anatomy, as for the shape, and as for the form of that patient alone. Each patient is a unique, right? And within the same person, if you put up age, and your bones getting deteriorated, and you will have a osteoporosis problem. So if you put up age maybe 40, 50, so then with the same person, if you put up the age, and your anatomy or your bone structure is getting changed, so then where we need to have a customized solution. So, and then even you have designed some implant, then it should be accurately place them. So then your physical models is going to play a vital role under these circumstances. I will try to demonstrate all these advantages with my case studies, all 6 case studies which I'm going to explain. So how do you get fabricate anyway? So then same old story, we need to talk about, say, subtractive versus additive manufacturing. So then that, if you see in a medical perspective, the subtractive versus additive, so definitely your complexity is a free of cost. That's what we have been using, that quoting that sentence. The complexity is a free of cost. But complexity, if the complexity is increased, and your conventional subtractive manufacturing methods will leads to 2 times, 3 times, 4 times cost if it is a simple geometry. So then you have an exponential increase in your the product cost, the fabrication cost, once the complexity has increased, right? And of course, all your medical um, products, or like your human anatomy is very complex in nature. Why? Because it's a God's design. So it's highest level of complexity. So in terms of, you have a lot of undercuts into the human anatomy, and you have a lot of voids inside, and you have a lot of internal geometries like neurovascular canals. So those are very tough to program or to machine. But the materials also brittle, soft, non-sterilizable. You have a lot of constraints or the limitations once you come to a subtractive process. But definitely 3D printing or additive manufacturing will simplify your job, and the cost effective also. So you can talk about the medical application development. Then how do you develop a medical application? So then under that, so probably you may have a two say routes, or the two methods, or two occasions, or two circumstances, like where you have a patient with you, or you may have a dry bones or a cadaver bones with you, or you have a prototypes or with you, the physical model or a patient, or the bone or whatever it is, those are there. And as we understood from the previous discussion also, if you are looking for only surface study, you want to get capture only the external surface, outer surface. So then you may use touch probe or laser scanners. That's what you have been talking about. And your region of interest, or your a study could be internal geometry or internal tissues. So then you may advise to undergo a CT MRI scan. But either it is a CT scanner or a reverse engineering scanner or a laser scanner. So data should be acquired from any sort of this a product. Then the data could be captured, acquired. That acquired data, either a kind of a image, a two-dimensional grayscale images, or a point cloud data in case of a reverse engineering approach. And you have a medical image processing tools, just now we are discussing, where it can process your images. Or in case of reverse engineering application, you do have a tools, reverse engineering tools, which it will process the point cloud data. And ultimately it may either you come this route or this route, and your job, your idea is to make an STL file, or VRML file, or IGS file, or a DXF file format. So then which you can get that data. And then you may use a free-form modeling software tools, or the CAD tools to ultimately make a geometric model or a nerves-based CAD model. And once you get that data, so your application is several folds. So just you need to fabricate a biomodel which it has been captured from the patient, or you need to make use of some surgical aid tools, maybe for supporting devices for elderly people, or maybe some template or some guide which you are designing to assist during the surgery. That is a customized guide or a customized template. So then you can even fabricate implant, or even you can make the tissue engineering scaffolds. So, or even you can make use of these models for planning the surgery, simulations of surgery, or FEA models, or medical devices. So maybe some sort of devices that it will assist during surgeon, maybe a cardiac surgeon, maybe an orthopedician, maybe a oral maxillofacial, craniofacial, or neurosurgeon, or ophthalmologist, or whatever, ENT, or whomever. So then we need to say make use of either a laser scanner or a CT MRI scanner, depending upon your situation. Some situations where you never have a digital data, like, so if your dentist might have taken impression from your mouth, and he might have prepared a denture, so which it has been collected from the patient mouth, you never have a soft copy, or you never have a digital data, and which we need to make use of this reverse engineering scanners to get it capture your anatomy, right? So, so then coming to the applications. So of course, 3D printing in medicine, we do have um, you can make use of this technology for fabricating an implant. Why 3D printing? Why can't it be a subtractive or a casting or a forging or welding technique? Why only 3D printing is so encouraging? Why? Because so you have companies like Anatomics, Jimmers, or Stryker. So these are the players in medical device or medical implant manufacturers. So why they are looking for 3D printing? So then what is the speciality in 3D printing? Of course, which you have wherever you have the bone or wherever you have the tissue or wherever you have the organ. So your 3D printing technology will mimic exactly the bone structure or the bone anatomy. Say you have a chest implant, so which it is almost mimicking the native bone structure, in terms of form, in terms of geometry, in terms of functionality some extent. Yeah, so and then even it can be a chest implant, or even it can be a spine wedge or a spine cage, which we can closely observe. This is a porous structure. So how do you get mimic this structure? That is patient specific. So then it may be varying. The porosity will be varying from person to person, and put up age, and again it may be varying, right? It is not a constant, it is a variable parameter. So then how do you match that? So obviously your 3D printing will enable you to do that. So that is the basic advantage once you talk about your implants. And then coming to surgical planning, so where your pediatric heart surgeon, maybe he or she has to operate a month's baby or a day's baby, the heart surgery has to be performed. So then how complex it is, and how say, and in the recent times, even the FDA or any other regulators, these regulator bodies, they are giving a certification for these sort of models for surgical aids or surgical planning. And even you can fabricate a lightweighted structures for an orthopedic cast. So we know the advantage of 3D printing mimicking the lattice structure, or mimicking the um, bionic designs, or topology optimized structures, or lattice structures, right? So where you can make a lightweighted structures, either it is an aerospace application or a medical application. So where, or your orthopedic application, where our focus will be mimicking the nature, or mimicking the biology, mimicking the what you call your, yeah, mimicking the structures of lattice or biological structures. So that's quite phenomenal, right? Or even if you talk about the pharma or drug delivery application, so you can personalize the medicine. So you can personalize the dosages of the pills. So as for the patient requirement, you can personalize them. So you can make use of this technology for personalized drug delivery system, right? That's quite interesting. So which even you have plenty of applications which we will be talking about, but let me confine the three areas in the form of 6 case studies I am going to discuss with you. So those are related to dental implantation cases, cranioplasty cases, and maxillofacial cases. But apart from these three applications, so which orthopedicians have been using this technology for the total hip replacement. So, and people may be using it for biomedical devices, fabricating the biomedical devices. and fabricating the biosensors and biomems devices, microfluidic devices, bioprocessing and bioseparation applications, and augmented tangible molecular models for research and education. Yeah, otherwise, we need to preserve these anatomical or cadaver bones or your dry bones. So typically, if you go to an anatomy class of a medical students, so which the preserving these cadaver bones are very tedious. But once you have a CT data, or as such you have some images, and you can print them and you can make use of your anatomy class or your say DNA, showing a DNA structures or demonstrating DNA structures, or whatever it is, right? Say which you will be say making use of these models for such sort of applications, maybe a conjoined twin application, oral maxillofacial reconstruction, the facial reconstruction, or the cranial implants, or the finger joints, or the knee joints, or again a femur joint, or prosthetics, or orthopedic applications, anywhere wherever you have your data that has been captured. So then left and right you can make use of those models as for your requirement, right? So irrespective of your medical specialization, so which it can be applicable. So then, so let us focus on our own experience with the doctor community. So these are the real time cases that we have been performing along with our collaborators. So right from the dental hospitals to oral maxillofacial to craniofacial people, I will try to say share my experience by making use of this medical image processing tools as such, and also 3D printing technology in combination with medical image processing tools with the 3D printing technology to solve a real time, say, cases, the medical cases or surgical treatments or clinical applications. I will try to say present before you in terms of 6 case studies. Um, right now, I am going to present 6 among the case studies which we have been doing it. And the first case study, it is a cranioplasty kind of application where we model and analyze the cranial implant. So normally these terms are derived from Greek and Latin. Normally, as we know that it's not exactly the English words, the terminology which you can come across. The cranial bone. Say, let me try to say give you the classification of bone. If you take your skull part, basically you have a lower jaw that is called a mandible, and you have a upper jaw that is called maxilla. Anything other than mandible and maxilla, so you have a skull portion, and in particular the skull portion which protects the brain, and you will be called that as a cranial bone, the cranial bone. So one of the patient met with an accident, and he lost or he broke this skull cranial area, the skull bone at the cranial portion. So, and the goal here is to design an implant which exactly it is getting replaced, or which he lost or which you broke during met with an accident, and which you are trying to make that part of the skull as in the form of implant, and it is getting fitted during a real-time surgery. So then, how do you get started this journey? So, of course, it should getting started with the CT data. So, which we need to so start with the CT, collecting the CT data from the patient skull portion, and by making use of this, we have used a mimic software to do this job, and we do apply thresholding, and we do a region grow, and we create the mask, and we say finally you are going to reconstruct your skull. But whereas we need to design an implant which it is getting missed here, this bone, then the challenge here is your thickness of the skull is not uniform across your bone, but we need to take a lot of measurements, and we need to design them. So for that matter, we have used two tools here. One is mimics, another one is a thematic software to perform this job. And one more challenge here, not only attaining the geometry and the thickness of the bone, and we need to ensure the the fitment of the implant versus the native bone, the skull bone. So that is why it is so important here is, you have a body fluid, you have a fluid called cerebrospinal fluid. So cerebrospinal spinal fluid is the fluid, so that will be generated, or that will be produced in the brain, and that the cerebrospinal fluid will pass or will circulate from brain to spine all the way. So if you have not done this implant proper fitment, the fitment of the implant is not done properly, and there will be a chance of leakage of that fluid, the body fluid. So which we need to say carefully design and carefully print that, and which we need to say ultimately ensure that your implant is getting fixed into the patient body without um, losing the tolerance or whatever your leakage. It should not leak your design, your implant, right? So this is the typical one where we need to, for that matter, we started designing, modeling the implant, and further we made a trial and error to fabricate different versions, first version, second version, third version of this implant. And even further, sometimes your some of the accident cases, or some of um, the fungus, or some sort of, you have a black fungus now. So you have all these things which were your defect, or your um, deformation, or your defect will be not always be the symmetric defect. So sometimes it may be a non-symmetric defect. Why? Because we don't know that may be with the trauma, that's through accident, or through some fungus, or some other malfunctioning. So which we need to develop our own algorithms sometimes, which your proprietary softwares may not be able to say give you the sort of features, or the sort of things, and which we need to develop our own algorithms, our own code to do reconstruct these surfaces. Maybe another aspect here is the fixation points. What do you mean by fixation points? We need to fix this implant onto the skull bone. And where do you fix it? Means, then what is the importance of fixation points here? So you have that fluid, as I said, that fluid has to exert uniform pressure onto this implant. So which it should ensure that it should be say such sort of it should not give a non-uniform pressure to the implant. So ensuring that that should be modeled, and that should be simulated, and that should be analyzed properly for this patient specific requirement. And then another aspect is material aspect. As we know that So not all the engineering materials are qualified for the biomaterials. Biomaterials may be hardly 10% or 15% among your polymer, metal, ceramic, or composite groups altogether. So then, whether all the 10% materials can it be 3D printable? So that is another constraint which we need to work, right? So you are going to make use of a 3D printing technology, and you may have 7 classes of 3D printing technologies, right from the VAT system to the extrusion system to the sheet lamination to the powder bed to the binder jetting to the material jetting to the uh, energy deposition DED systems, that is direct energy deposition systems. You may have 7 groups of technologies, but not all the things, all the machines can capable of printing polymers, metals and composites and ceramics. But certain technologies can print certain materials, then which we need to check our own facility, and then the technologies that are available with us to print them, right? So we consider the polymers like a peak, that is either ketone and polymethyl methacrylate, PMMA is a polymer group, and titanium 64 is the metal considered, and we analyzed for the deformation and equivalent stresses for that, and which under available facility and the materials. And then finally it should be getting printed, and that it should mimic the bone, native bone structure. And if you see this the skull bone, you can find a sandwich kind of a structure. It is not uniform solid bone, but it never, so it's going to be a sandwich kind of a structure where you have the inner bone is around zero point 0.8 to zero point 0.9 thickness, and the outer bone is around zero point 0.5 to zero point 0.6 and in between you have the porous bone structure, and again varying porosity and depends on the patient condition, and which we need to mimic them, right? So then none other than 3D printing technology can replicate, can mimic, can customize, can personalize this sort of implant, right? So that is the advantage where we can get out of this technology. And then let me move on to the next case study. So that is a second case study, is a dental case study. Then how these models, especially 3D printed models, are helpful for placing an implant or designing an implant or fixation, implant placement and fixation, and how this technology is helpful. Say why 3D printing? Otherwise, you forget about the 3D printing. 3D printing has come maybe 30-year-old technology, 31-year-old technology. But whereas what was the previous or the conventional or traditional practices they adopt in a dentistry, right? So if you want to place an implant, uh, he requires 2 implants, a 19-year-old boy, and which incidentally he lost 2 molar teeth, and which 19-year only, but is not 40 or 50-year, when which we need to um, place an implant, and which we need to keep the teeth onto the abutment and things like that. But conventionally what they do, probably they take an impression from the mouth by using some plaster of Paris kind of a material, like they will take a denture, the cast, dental cast from the patient mouth. But the biggest problem with that is with the dental cast or with that impression technique, you never get the information about the nerve, that is inferior alveolar nerve or the root canal. So that is inside the bone, but it is not outside the bone. You will get only the outer surface when you take an impression from the mouth. So but you may be much worrying about this nerve information. Why? Because he or she over drills, and there will be a chance of cutting this nerve, and under drills the the um, the implant may not be fixed firmly. So then what could be the depth of the drill that we need to drill it, and what could be the diameter of the drill, and what could be the orientation, right? And all that stuff. So once you have your model, the patient model, that taking a CT scan of the lower jaw, the mandible part, and further it is getting 3D printed. So, and you can take this model, and you can sit with the dentist and let him rehearsal the surgery. So what is the size of the drill bit he is going to use, and what is the size of the length of the drill, diameter of the drill, and orientation of the drill bit and the implant. So he or she can do that, so before he go into the actual operation theater. And eventually, so you can customize the implant, not taking a standard implants that are available from the market, like maybe from Jimmers or maybe any other player. So which there may be a standard sized implants are available, but you never get a customized solution from these standard implants. So which your 3D printing can give you a kind of customized solution here, and placement, and then further fabricating it and fixing it, and finally it is getting say fixed onto the patient mouth. So, and that's about the second case study. And the third case study which I'm going to discuss with you is a mandibular distraction osteogenesis. So this is a once kind of a surgical procedure, distraction osteogenesis. So what do you mean by this? So mandibular is a mandible is a lower jaw. So it is a lower jaw. Distractor is a device. So basically, a distractor is a device which they use for guiding the bone growth. Actually, bone will be having the natural growth and depends on the age, sex, and other factors. So, and you will be doing an osteogenesis kind of stuff, means basically what you're going to do. So you cut the bone and leave the bone, leave the space, maybe 2 mm, 3 mm, 4 mm. So keep on stretching the bone. Ultimately, our aim is to reconstruct the bone. So that is the our job, to lengthen the bone or to stretch the bone or to twist the bone, right, by making use of the distractor. So that is an idea, that is a conventional method of doing a oral maxillofacial surgeon. But how 3D printing is helpful here? So why 3D printing, how it is getting helpful, that's what so here we are going to discuss, and how 3D printing is helpful for performing this kind of reconstructive surgery. So you take this 8-year-old girl, and which you can see, are you able to see the abnormality, the abnormal growth of the bone, the lower jaw, the mandible. Because of that abnormality, she could not open her mouth completely, that is 4 to 5 centimeters, and which we can see an asymmetric form of the face because of that abnormal growth of the bone. So, and you can see the other orientation of this patient, right? And again, which we need to get it started with taking a CT data, capturing it and reconstructing it, and further, which this um, CAD model is further is being printed into by using a 3D printing technology. But anyway, I will come to that. I'm talking about this distractor. So what they do is they cut the bone, and they um, leave some space here. So, and then bone will be having its own growth, and you may be guiding, they may be guiding the bone growth through this distractor. So this distractor device is kept inside the mouth, and this will be a screw kind of a distractor, and which it can be the patient can turn this revolution. So then the bone will advance, and then the bone growth will be done. So then typical calculations, then how much length it should be getting stretched forward, and whether it should be twisted. Say for example, you take this case, that girl This is the model that has been printed through FDM based printer and is in ABS material, in which we can see the abnormality, and which you are trying to twist this bone, right? And not only twisting this bone, and our aim is to get ensuring that the symmetricity, the abnormality which it should be, say, and if you see the other orientation, the ramus height, this is called as a ramus height. This ramus height from the healthy side versus the defect side, the defect side is not grown up to this healthy side, right? Which we are able to see this ramus growth. This ramus growth has not happened. This is the healthier side, and which we can calculate how much length it should be getting stretched, right? And how it is getting stretched, and how much it getting twisted, what is the twisting angle, right? So all that will be calculated, and all that, based on that, you design that distractor, and that is specific to this patient, right? And this is before the surgery, and then this is after the surgery, and still we can see this is during the transformation, and still you can see there is a distractor here. And you may wonder why this is not properly, say, done, right? So yes, you are correct. So the bone growth will be there up to 19, the teenage. So it has been overcorrected. As of now, it has been overcorrected, and it should be further done the final correction once she turns 19-year-old. So this is the typical situation where your 3D printing technology can help the surgeons, so to devise a distractor, or to devise, to um, fabricate some sort of things, or some planning the surgery, or those sort of applications which we, if we can, you make use of these models, right? And even the next case study I'm going to discuss with you, the fourth case study, is amyloblastic fibroma of mandible, or this is an cancer case, which I intentionally pick one cancer case. So this is a cancer case, and the patient having a cancer bone, and which it should be reconstructed rather than it should be removed, the bone from the patient mouth. So, and which you can see this portion from the X-ray image. So where it should be. So then again, which we need to start with taking an CT scan of the patient, and our, anyway, this is a cancer bone, we need to cut this bone. And once you cut that bone, you should not leave that bone as it is, and then which we need to try to design some implant and try to augment that portion wherever you have removed that bone. So then you can make use of the mirror option, and then this everything we have done through mimics and thematic software. And this will be, say, done to copying this portion from the survived to the defect or the cancer side, from the survived to the cancer side. It has been copied, the form, dimensions, and everything. And further, it is getting 3D printed and checking it, how much portion they have to cut, and they can rehearsal, they can practice that portion where they need to cut. And that sort of experience, or that sort of feel, that sort of confidence, that the surgeon is almost doing a real time surgery, you can have such a feel, right? Why? Because it has been derived from the patient mouth itself, right? And then which we need to design an implant here. So, and then we need to attain the nerve relieving capability also. What do you mean by nerve relieving capability? So you have the root canal, or the alveolar inferior canal, which it will pass from this condyle portion, and we need to relieve that. Relieving option should be given. This nerve has to go along this implant, and it should touch this mental foramen, and it should come out from the other side of the condyle, right? And then, which again, we will be taking the help of survived side to the defect side for designing your implant. And we want to make it more lightweighted designs, right? And we can take a lattice structure to enhance the osteo integration between the bone and the implant, to formation of tissue easily, and the osteo integration between the bone and the native bone and the implant. So that is the advantage here, 3D printing, which you can make use of these lattice structures, incorporating a lattice structures, not only lightweighting, and it will mimic the bone structure, or it will enhance the osteo integration or the tissue formation, right? And the next case study I'm going to discuss here is the TMJ ankylosis, that is temporomandibular joint ankylosis. So this TMJ ankylosis, if you ask any oral maxillofacial surgeon, so and then what is going to be the toughest surgery in oral maxillofacial department, it is none other than TMJ ankylosis or the TMJ reconstruction. What do you mean by TMJ? So that is temporomandibular joint ankylosis, means you have a joint here where you have a lower jaw and you have a upper jaw, and where it will form a joint here, and because of that joint, so the joint on the left side and joint on the right side is responsible for opening the full opening of the mouth. So that is 5 to 6 centimeters opening, normal opening of the mouth. So that is responsible. Your TMJ joint on either side is responsible for healthy person to open 5 to 6 centimeters normal opening of the mouth. But unfortunately, um, this patient, she had a birth problem. She had a birth, by birth, she had a fusion of that joint on one side. The other side is survived side is okay, but only this defect side is. Our idea is to reconstruct that joint. So by taking the help of, God has given a hint that the survived side which we are targeting, and we are trying to copy the same form, geometry, dimensions, everything from that side to this side, and retaining that, the reconstructing that joint, right? And this is what I'm talking about. Why it will become very complex surgery, the TMJ ankylosis, is you have a nerve system also. I'm talking about, so this joint is free from fusion, and then only he or she can articulate, right? And normal biting, normal chewing, and normal articulation, occlusion. So it will take normally, but once this joint got fused, so where you have a zygomatic arch, this zygomatic arch is from um, uh, the maxilla side, and you have the condyle from the mandible side, and where it will form a disc or a joint at this fossa component, right? So this is what which we need to release this joint. We need to disconnect. Why? Because it has become integral part. She could not open her mouth even as 1 centimeter also. So that is, she has been like that for the past 21 years, right? Yeah, this is what I'm talking about, which we have. This should be getting dismantled, or this is getting fused, and which we need to taking the help of the other side, and which we are trying to redesign this joint. So that is the intention, and this is what I'm talking about, where we have copied this, uh, say transformed this dimension from the survived to um, the defect side, and this is the design, the condyle only I'm talking about, and which we need to make three parts, and one is the condyle from the lower jaw, and this is the design. And initially we printed with the desktop based polymer printer to know the form how it is coming. And again, the fusa component is also say copied from the survived to the defect side. And this is the fusa, and this is the design, and this is printed in a polymer, a biocompatible polymer material. And finally, so this joint looks like this. So this is the zygomatic arch, and this is the condyle, and it will form a joint here. And ultimately, this is getting fixed through the screws, with the help of the screws. And for that also, we have designed a template or a guide for easy drilling of that holes with the help of that um, guide. So this is what it's going to be, and this is the guide I'm talking about. So this guide has been designed for the patient specific, and it has been um, used during the surgery, and which we can see once this fusion of the joint TMJ is released, and which we can see now, she could able to attain her normal opening of the mouth. So that is say 4 to 5 centimeters, so she could able to attain. But she has been like this for the past 21 years. And whatever I showed you, that is 3D printed implant through a metal 3D printer, titanium 64 is the material used um, here. And then this is fixed onto the maxilla side, that is the upper jaw side, and from the lower jaw side. So this is the joint with the screws, and which it is got fitted. And now we can see she's doing good now. Even she could able to open her mouth, normal opening 5 centimeters, and normal biting, normal chewing, and normal occlusion, and all that she has attained. So for the past 20 years, she has been leading her life in that way. So she had a better societal life after 21 years. So that is thanks to the technology like 3D printing. So which it has changed her life. The societal life of the people is getting changed. Not only um, non-living things like a products like car or automobile or aerospace, right? So but human beings can also be getting repaired, or can also be say given a different a new life to the living beings, right? And let me come to the last uh, case study. So that is a Basilasio integrated implant. So this Basilasio integrated implant, so uh, this case, it is accident case, and he met with an accident, and incidentally he damaged the upper jaw bone, and and he lost the 5 teeth on the upper jaw side. And we need to attain the nerve relieving also here. And more or less it is in a asymmetric fracture, which you can notice it. Why? Because it is accident, we don't know whether he is going to broke his bone symmetric way for ease of your modeling and design, no, right? So it is a asymmetric design. And why I'm talking about asymmetric design, there is a thing here, right? So if you have a standard implants, standard sized implants available in the market from gymmers or any other people, you can buy these implants. These are the standard sized implants. So if at all, if you have a bone support here, and you can use one-to-one implant and you can fix it. But that is not the case here. You don't have a bone support here that it would be fixed all these 4 or 5 to against the 5 teeth, no. And more or less you don't have much space here, bone support here, and absolutely your the standard implants are won't work out, which we need to design our indigenous implant. And that too, as such, how he has broken is a asymmetric the nature of the fracture. which we need to design as for his thing, and then which we need to test for the failure of this um, say implant and fitment of the implant, so which we have done by using thematic software, and which we have checked the fitment of this implant. And further, which it is getting say printed through bus. First we need to know the form, and we need to check how it is coming, implant versus the bone. So that's what initially we printed with a desktop, a DIY kind of a printer, not even a commercial printer. So we have printed with the polymer, the PLA based desktop printer, a DIY kind of a printer, to know how it's coming, and then and giving it to the surgeon to say fix. How do you get fixed during the surgery? And he's going to use those tools and fitting it here, and finally it is coming in this way. And at least we could not accommodate 5 teeth, but 4 teeth has been accommodated. And this is what where the implant is got printed in a metal 3D printer with the titanium 64 with the powder bed system, which we have at our NIT Warangal facility, and which it is getting printed, and which along with the supports which you can see here. And after removing the supports and sterilization and following the FDA standards to autoclave and other formalities of for this to implant it. And this is during the surgery where you can see this implant got fixed snug fit inside the a patient mouth. And this case study we have published in a rapid prototyping journal, which this is an indigenous implant. You cannot buy this implant, right? Say you can buy only the standard sized implants, but not this. So this is after this is the post surgical X-ray image, which it has been captured and check the orientation and fixation of this implant. So which is there at the backside, permanent implant, lifetime implant, and on top of it, where you can see the abutment and when fixing these 4 teeth under the patient mouth, right? So in this way, where even you can find several the complex cases like abnormal growth of tumor, which you can see how the conventional surgical procedures will say how do you operate it. And you have a lot of cleft cases by birth, lot of cleft cases or some head injuries. Then you wherever you find some complexity in the surgical, conventional surgical, traditional surgical procedure, and 3D printing is SOS for such kind of situations. And what could be the future? Let me conclude. Why? Because we have already touching 2 hours of presentation. So let me conclude the session. So what is the future direction of this medical 3D printing? Undoubtedly, it's going to be the organ printing. So what is an organ printing? So far we are discussing so the bone replacement or the bone substitute, but is it the way in future? But definitely in future, so it may be the replacement of the complex organs like a heart or a liver or a lungs or a kidney, so any complex organ. So what could be the material in that case? Is it the same man-made material, synthetic material you are going to use? Absolutely not. Absolutely not. Why? Because the material could be a natural material, or it could be a living cells that it might have taken, or a piece of heart or a piece of liver might have taken as your material, and it may be getting multiplied by doing some cell cultivation, and then finally you may be printing it, and you may be introducing inside again, putting back into the patient body, maybe wherever you have an organ that is getting replaced or that is getting say repaired. So whatever the way you want to do it. So let me summarize what is an organ printing or a bioprinting is all about. Say you have certain organ that you're targeting it, and you extract the cell from that organ, and you add the nutritions and you add the proteins, and you do a cell cultivation, you multiply these cells in an incubator and you grow it, and that as it is, are you going to implant it? No. Then we need to ensure that whether it has a sufficient mechanical property, it has a sufficient biological property, and it has a sufficient rheological kind of a properties, or all sort of properties. Then how do you get checked whether those properties are on par with the native organs, right? That's a quite challenging task here. You do operate you do use some bioreactors to do a sort of what you call testing it, and you can do that, but whether is that or on par with the native, that's the quite interesting scenario, right? So then what is the state of art of this argon printing or bioprinting? People has already successfully regenerated, means basically it's a regenerative medicine, right? So people are already successfully done, bladders has been replaced or regenerated. um, like skin is also, people has been regenerated, and blood vessels also people has been um, regenerated. But if you talk about organs like kidneys or liver or lungs or heart, so then quite challenging organs or quite complex organs, right? The functionality, as far as functionality is concerned, it's very tough to retain. But then the time may be the answer for this. We can find a lot of breakthroughs in this direction in the recent times. So then time may be the answer for this. Maybe down the lane, 10 years, 15 years, maybe 20 years, maybe you can expect a lot of breakthroughs in this direction. So yeah, let me conclude my talk. Let me summarize what I have done for the past 2 hours. So we have started with a general medical 3D printing procedure, and we have thoroughly discussed various medical image data processing tools like mimic software or thematic, or it can be a 3D slicer software or imageware. You may have several simpleware or 3D doctor, waxm. You have plenty of medical image processing tools, and you do have a reverse engineering tools though, and you have data formats which we thoroughly discussed like STL, AMF, 3MF, or .obj files. And then you have we have discussed thoroughly the importance of these physical models in medicine, like for planning the surgery, rehearsal the surgery, or implant design or prosthetic design, and so on. And medical application development, how do you develop a medical application using 3D printing, that also we have discussed. And importantly, we have discussed a real-time medical case studies, around 6 case studies, and how we have say achieved, or rather than say collaborating with the hospital people to serve some people at least by using this technology. And we have given the future direction of this medical 3D printing technology. And before I hand over the proceedings to the organizers, so let me thank my team of people. This is a team effort, right? So which we independently, you cannot do this research. Basically, the requirement should come from the clinicians. Like we have a very good team. We would like to highly acknowledge the Shekhar Reddy, Dr. Shekhar Reddy, and Dr. Aditya Mohan from Panniya Dental Science and Research Center at Hyderabad for their support towards oral maxillofacial, craniofacial surgeries, and then the dental support from Dr. P. Mahesh from Narayana Dental College, Nellore, and the financial support from two of my projects, DST and SCRB, for the financial support. And of course, last but not the least, my UG, PG, and PhD scholars who really do their part of their research work. And I may be presenting here. You might have noticed all the citations of these PhD scholars or the PG or UG boys, and of course the PGs from the hospitals also are highly acknowledged here. And coming to the facilities which we have AIM facility, and we are the people started first time in India MTech in additive manufacturing specialization. So which we have been using these facilities for supporting that course. We have a metal 3D printing facility, that is the DMP Flex metal 3D printer from 3D Systems USA, and we have a Dimension FDM, a Stratasys make machine, and we have another Stratasys make Mojo machine, and we have a Ultimaker 2 Plus as a desktop printer. And apart from this, we have other DIY kinds of printers, and we do have two scanners, AnyScan and a Sense scanner, and muffle furnace and short peening machine for post processing of this metal 3D printing, and of course for the other polymer based systems also we do have post processing equipment. And apart from this hardware, and we do have a software exclusively meant for the additive manufacturing and 3D printing facility. We have a Mimic software, we have Magix, we have a Thematic software, we have a Catalyst software, and we have a 3D Expert software to simulate the metal powder bed system technology. So we do have a 3D Expert software from 3D Systems USA. So these are some of the facilities we have. Yeah, I think I have done from my side, and we do have a YouTube channel, and if you are interested, you can visit us and you can subscribe us also if you are interested. So I may be leaving this the link, YouTube link in the chat box, so you can even see that. If you are interested, you can visit that also. So I have done from my side. Dr. Yogesh, it is over to you.
Okay, sir. Thank you, sir.
So if anybody's having certain questions,
any participants are having any questions, so you can quickly ask, sir. Anybody has any question?
I think chat box, I can see some questions here.
Yes,
can
sir.
I answer that?
Yes, you can.
This Mishra is asking, sir, please suggest the implant material for human bone lower limb. So human bone, if you are targeting better, you can go with ceramic. Maybe you can go with hydroxyapatite, um, calcium phosphate, maybe ceramic may be the right choice for you. And then for that, you can go with the binder jetting systems. Yes, yeah, you can look for that material. It is hydroxyapatite, and go with the binder jetting. Is quite convenient to process ceramics, bioceramics like hydroxyapatite kind of stuff. And somebody's Deepti Ranjan Saho. Sir, what could be the lifespan of those screws? Do they need to be adjusted in future? Because as you said, bone grows. No. No, actually that I'm talking about the distractor, but distractor is not a permanent device. So that distractor will be used during the transformation of that bone growth only. So that is not a permanent device. It's just for the 2 months or 3 months. So that is the external device. Then we are going to remove that. It's not going to be an implant. Just it is a device, supporting device for growing the bone, but it's not. Yeah. So the screws and all. It's just a temporary device. It's not a permanent device. It more or less it's not an implant. It's a device which is external device. Yeah, and I can see Santosh Patil. The work is really extremely congratulations. Okay, bone scaffold work is being done in Manipal, Jaipur campus too. Okay, great. Very informative session. What is the challenge work? Okay. What would be the lifespan of those screws? I think, yeah, I have the same question. Is it repeating?
So same
Yeah,
question is there.
yeah, I think, yeah. If anybody is having, you can unmute and you can ask that also. Yeah, I think I have
Anybody is having
answered.
any questions, so you can quickly ask. So I think they have already written their questions.
Maybe they might
So
have exhausted about.
no. So it is very extremely good lecture you have delivered at our institute. So thanks very much. And you have shown us the application of 3D printing, especially in the biomedical engineering applications. We are not familiar with this one, and none of the speakers have thrown light over this. So, especially, I have chosen you have given me on email that these are the topics you want to deliver. So, I especially have shown this the application of biomedical engineering on 3D printing, because no other other speakers are also they are also doing well, but they are not showing on the specifically on the biomedical applications. So you have shown us the especially the case studies which the ATAL FDP has requested. So that we have to show the case studies during the this ATAL FDP. So you have fulfilled this requirement also. So thanks a lot for accepting our invitation to
Thank you.
deliver such a nice talk in our ATAL FDP. And we will look forward to invite you in other technical programs which will be organized in future in our institute. So thank you. Thanks a lot, sir, for joining us.
Thank you. Thank you for the opportunity, Professor Yogesh. Yeah, thank you. Thank you, one and all. Take care. Bye bye. Yeah. Thank you.
You can leave.
So, yeah, I'm
So,
leaving. Yeah.
so participants, I will be sharing the link feedback link in the WhatsApp group just after a few minutes. So now I'm stopping the session for day 3.